Hello and welcome back. Let us understand what is singular value decomposition. I said singular value decomposition is a more generalization of eigenvalue decomposition. We will understand why that is. Okay. So eigenvalue decomposition can be done on a square matrix only. Singular value decomposition can be done on any matrix of size m by n where m is not equal to n. So when you decompose a matrix C into U sigma V transpose, the singular value decomposition, you get a U and V an orthogonal matrices and sigma are the square root of eigenvalues. The eigenvalues matrix square root is the sigma. So why it is and how it is, let us see. So I have taken, I have taken a matrix C, and if you want to decompose that matrix into U sigma V transpose, I will make two statements. The first statement is, to find out V, you need to find eigenvalues and eigenvectors for C transpose C. The second statement, to find out U, you need to find eigenvalues, eigenvectors for C transpose. I made two statements. First statement is, to find out V in your singular value decomposition, you need to find the eigenvalue eigenvector decomposition of C transpose C. To find out U, you need to find eigenvalues eigenvectors of the matrix C transpose. I said singular value decomposition is a more generalization of eigenvalues and eigenvectors. This is what it is. You are finding eigenvalues and eigenvectors only, but not to the direct matrix C. You are calculating a correlation matrix between the features and the correlation matrix between rows and trying to decompose that as eigenvalues, eigenvectors, because when you calculate C transpose C, you get a square matrix. What is C transpose? N by M. If your matrix C is M by N matrix, the dimensionality of C transpose is N by M. When you multiply C transpose with C, N by M into M by N, you get N by N matrix, right? N number of columns are there, you get N by N matrix, and you decompose that into eigenvectors and eigenvalues. You get a maximum N vectors of size N, right? So the V is going to be of size N by N and U is going to be of size M by M, because if you multiply C with C transpose, what is C? M by N. C transpose is N by M. When you multiply these two matrices, right, you will get M by M, number of rows by number of rows matrix. That's a square matrix. You can actually calculate eigenvalues and eigenvectors. So you get U and sigma transpose and sigma square and U, right? That when you decompose C transpose, right, you get U sigma square U transpose. So we have to find sigma. So when you apply square root to whatever decomposed matrix here, the eigenvalue decomposed matrix, you get the sigma for your singular value decomposition also. It is a simple trick. You are getting it, I think, right? So that is what the singular value decomposition is. If we want to see the proof, why this guy is trying to talk like this, he is saying singular value decomposition and again eigenvalue eigenvector decomposition. It is simple. Let us see. Suppose that that you decomposed C into U sigma V transpose. You already assume that for your matrix you already have U sigma V transpose. When you do singular value decomposition, what is U? An orthogonal matrix. V, an orthogonal matrix. You already thought that, right? So when you actually calculate C transpose C, what happens? What is C transpose? C is already a decomposed matrix, U sigma V transpose, right? You substitute C here and whole transpose and C. What is C? U sigma U transpose. We supposed that already it is decomposed, right? When you AB transpose is equal to B transpose A transpose. That's a matrix property. So we will switch these V transpose whole transpose, sigma transpose and U transpose. I actually flipped it because I transposed, right? So U transpose U is I because U is an orthogonal matrix, as C is already decomposed, singular value decomposed into this. We are assuming that the formula is already there or decomposed, right? U transpose U is I. So you got V transpose transpose. When you transpose a matrix and transpose it again, you get original matrix, right? So V. And then sigma and sigma are sigma square, because sigma is a diagonal matrix, right? And when you multiply two sigmas, right, you will get sigma square only. See this? Multiply this with this and this with this, 0. Sigma 1 square plus 0, 0 plus 0, 0 plus 0 and 0 plus sigma square. So you get sigma 1 square 0, 0. So you can call it as capital sigma square. This lambda square, sorry, this sigma square, right? So that is sigma square. V sigma square V transpose. What is this? It's a decomposition, right? So C transpose matrix, you take it and decompose it, you get three matrices which are nothing but V, sigma square and V transpose. That's it. Okay. And similarly the same thing. C transpose. What is C? U sigma U transpose, because you are already decomposed, right? You are assuming that you are already decomposed and you substitute it. And this transpose actually flips. V transpose V, right? V transpose whole transpose is V. So it becomes V transpose V, it is I, U sigma square V transpose. When you take C transpose matrix, you take the original matrix, calculate C transpose and calculate eigenvalue, eigenvector decomposition, you get U. You get three matrices, right? V sigma V transpose are, V inverse. V inverse and transpose are same, because U and V are orthogonal matrices. V is an orthogonal matrix, that means V transpose is equal to V inverse. In a eigenvalue decomposition, a matrix A can be decomposed into V lambda V inverse, right? V lambda V inverse. Lambda is nothing but sigma square. If you have to find sigma, right, which is equal to square root of lambda. So V transpose and V inverse are same, because V and U are orthogonal matrices. We already said that V and U are orthogonal matrices. So whether you put inverse here or transpose here, it doesn't matter. So to find out singular value decomposition matrices of a matrix C, first you need to calculate C transpose C and then do eigenvalue decomposition. You get V. You need to calculate C transpose. Need to do eigenvalue decomposition. You get U. That's it. Sigma square. You already got. You apply square root. You get sigma. That's it. Done. Thank you.